Have you ever like noticed how AI agents kind of get stuck doing these really basic tasks?
Yeah,
The kind of things that make you wonder, like, shouldn't they be able to handle something, way more complicated by now?
right.
What if they could actually adapt, genuinely adapt and tackle like these super intricate problems with the kind of like resourcefulness that you see in a programmer, like debugging a really tough piece of code?
I think that feeling, like that sense of untapped potential, it's really at the heart of a lot of the excitement and the advancements in this field, right? Like we
Yeah.
have these like insanely capable language models, but actually translating that linguistic understanding into like effective action in the real world, that's been a challenge.
Totally. And that's what makes today's deep dive so fascinating. We're going to be looking at some like really cutting edge research, especially your notes on the CodeAct system
Yeah.
and excerpts from this ICML paper. It's called Executable Code Actions Elicit Better LLM Agents. And basically, it proposes this much more powerful way for AI agents to operate.
Yeah, and your notes are really interesting because they pinpoint that core novelty, right?
Yeah,
It's not just about enabling AI to use tools. It's really about the fundamental shift in how those actions are actually conceived and executed, and
exactly.
like the cascade of implications that follow from that.
Exactly. You were really interested in like the fundamental why behind Kodak's innovation. Like what makes it different from other attempts at, giving AI agency.
Right.
So our goal today is to really unpack CodeAct, to understand this new approach to LLM agent actions and explore what this new paradigm really means. So we want to like grasp the core ideas and its potential to push the boundaries, but without, getting lost in the super technical weeds.
Yeah, absolutely. And just to kind of set the stage for everyone, the sources we're looking at today are your detailed notes. All notes 2025329, which gives us like a really good timeline and lays out the important concepts. And then those excerpts from the ICML paper, which that gives us the actual like research and the data, backing all this up.
Okay, so to really get why CodeAct is causing such a stir, I think it helps to take a step back.
Yeah.
Before we had these, super sophisticated large language models acting as agents, what was the situation?
Right.
And how were people first starting to think about letting these LLMs take action in the world?
So, in what your notes accurately termed the pre-LM agent era,
Yeah,
large language models were very much text-centric, right? And
right.
like their capabilities were really all about understanding and generating human language, writing text, understanding text, and their ability to actually interact with the world outside of that, like in a proactive way, was pretty minimal.
Right. So masters of language, but kind of passive in terms of real world engagement.
Exactly.
Then came what you've labeled the early LLM agents. How did things start to change then?
So this was a period where we saw what are called action modules
Right. Right.
starting to be developed. And the idea with an action module was to take these LLMs and basically give them a way to interface with external systems.
Okay.
So think about things like calling APIs to get certain functionalities, or managing data in memory, or even like very rudimentary attempts at controlling like a robotic arm or running like an automated science experiment.
Got it. So the initial efforts were about giving them these very specific ways to interact with predefined tools.
Right.
So how were these actions actually like formulated and carried out?
So generally, these early agents would basically express their intended actions using like structured text formats.
Okay.
So think JSON, right?
Right.
And they'd have to adhere to very specific schemas that were dictated by whatever tools they were interacting with.
Got it.
So imagine, an agent wants to schedule something on a calendar.
Yeah.
It might generate a JSON object with specific fields for the date, the time, attendees, and all of that is like very precisely formatted according to how the calendar API expects it.
Okay. So I can see how that works for like isolated, well-defined tasks, but what were the limitations of just relying on these text formats?
Right.
Why wasn't that like the be all and end all solution to agent autonomy?
Yeah, and the paper actually points out two like really key limitations here.
Okay.
So first, constrained action spaces.
Okay.
Because those actions had to fit into these like very rigid predefined structures, what the agent could actually do was inherently limited by what tools were available and the very specific ways you could use them.
Yeah.
And then second, restricted flexibility, especially when you're talking about tasks that require you to use multiple tools in a sequence,
Yeah.
or maybe where you need to adapt what you're doing based on like the results of a previous step.
Right. So if a task required a bunch of operations using different tools or like the outcome of the first step influenced the next steps, these static text formats just wouldn't be adaptable enough.
Exactly. Yeah.
And your notes also highlight this phase that you call the emergence of code generation for control as a really important precursor to CodeAct. Can you talk a little bit about that?
Yeah, absolutely.
Yeah, so at this point, researchers started exploring, hey, what if we get LLMs to actually generate code,
Right.
like executable code, primarily in Python, to like control the behavior of systems like robots or maybe virtual agents in simulated environments. And this seemed way more expressive than just simple text commands.
And what's significant here is that it really marks a move towards using the inherent power of like programming languages to actually have control over these things.
Right.
But as the paper points out, those early attempts usually relied on these like pre-specified control primitives.
Okay.
So basically a limited set of pre-built code snippets that the LLM could kind of stitch together.
Got it.
And there was a lot of reliance on like very carefully hand-engineered prompts
Okay.
to try to steer the LLM to generate the right code. And often these systems just couldn't really dynamically adjust based on the feedback they got from the environment. It's like giving a chef just a handful of pre-chopped vegetables
Right.
instead of letting them actually choose and prepare their own ingredients.
So they were generating code, but still within a pretty limited framework
Yeah,
and lacking that real adaptability.
exactly.
And that brings us to CodeAct.
Right.
And this feels like a much more radical departure.
Yeah.
So what is like the big idea behind CodeAct? What's the core principle?
So this leads us to like the heart of the innovation, right?
Yeah.
So CodeAct basically changes the game by letting LLM agents generate executable Python code as their actions.
Okay.
And this is what the paper calls the unified and more flexible action space.
Right.
So instead of being stuck with these predefined text commands or these JSON structures, now the agent can write and execute actual code to interact with the world around it.
So the LLM essentially becomes like a programmer, like a dynamic programmer in real time,
Right, exactly.
which sounds extremely powerful, but also raises all these questions about complexity and control.
Right.
So what are like the key architectural innovations that make CodeAct work?
So there are a couple of really interconnected innovations here that kind of work together.
Okay.
So let's start with dynamic action adjustment.
Okay.
So one crucial thing about CodeAct is that it's very closely integrated with a Python interpreter.
Okay.
So the agent doesn't just generate code, it can actually run that code immediately.
Got it.
And the output of that execution, whether it's like the successful result of a function call or even like an error message, it all gets fed back to the agent.
Okay.
And this feedback loop allows the agent to either refine its previous actions or come up with completely new ones in the next turn of the interaction.
So that is so different from what we've seen before.
Right.
So if the code the AI writes causes an error, it can actually see that error and try to fix it in its next attempt,
Exactly.
just like a human developer debugging their code.
Right.
And the paper says, let me see, integrated with a Python interpreter, CodeAct can execute code actions and dynamically adjust prior actions or admit new actions based on observations, for example, code execution results that it receives through multiple turns of interaction.
Yeah.
So why is this dynamic capability such a big deal?
So if you think about it, it introduces a level of like iterative refinement, right? And like adaptive problem solving that we haven't really seen in earlier agent systems.
Right,
It doesn't need to figure out the perfect action right away.
right.
It can experiment, get feedback, and then slowly refine its solution through a series of steps.
Right.
And this is really important for these complex real-world tasks where you don't know the best course of action from the start. So it's not just trial and error. It's like the AI is actually developing this debugging process, a level of self-correction that we just haven't really seen before.
Totally, totally. And the next big innovation, you mentioned this leveraging existing software packages. And this seems like it could be huge for expanding the agent's abilities.
Yeah, absolutely.
So instead of being limited to just a few custom-built tools, CodeAct can actually use like this giant library of ready-made Python libraries.
Right.
So think about libraries for like data manipulation, scientific computation, web scraping. I mean, the possibilities are basically endless.
Yeah.
And the paper actually says code actions allow LLMs to leverage existing software packages. CodeAct can use readily available Python packages for an expanded action space instead of handcrafted task-specific tools. It also allows LLMs to use automated feedback, for example, error messages, implemented in most software to improve task solving by self-debugging its generated code. So the big takeaway here is the sheer range of what's possible with this, right?
Absolutely. It's not stuck with just a few tools that were made specifically for it. It can tap into this enormous amount of software that's already out there, which just completely changes how much it can potentially do. And you mentioned like the self-debugging through those automated error messages from those packages.
Yeah,
Which is like really clever, right?
right.
Because it gives this mechanism for automated learning and improvement.
Okay.
So when the Python interpreter like throws an error, it tells the agent exactly what went wrong. And since these LLMs are trained on so much code, they often already know how to read those messages and use them to fix their code in the next attempt. It's like having a built-in automatic debugging assistant that helps the agent find the right answer.
That's incredible.
Yeah.
So what's the third big advantage? You said something about LLMs already being familiar with code.
Right. So the paper actually highlights this. It says code data is widely used in pre-training today's LLMs. These models are already familiar with structured programming languages, allowing cost-effective adoption of CodeAct. So basically, because a lot of today's LLMs are trained on these massive data sets that include a ton of code,
Right.
they've already developed this really good understanding of programming concepts and syntax, how to write code, how to read code, and even common ways to use different libraries.
Got it. So all that pre-existing knowledge makes it way easier and more efficient for them to actually generate and reason about code as actions rather than having to learn a whole new, limited action format from scratch. So it's like they already speak the language of computation.
Exactly.
So that's really smart. And then the last key innovation, you talked about this built-in support for control and data flow within code.
Right.
Can you kind of unpack what that means and why it's important?
So this is where the expressiveness and power of using a full-fledged programming language like Python really comes in.
Okay.
Unlike those more limited formats we were talking about before, like text or JSON, Python just naturally supports these complex logical structures.
Okay.
So things like if-then statements or loops, those are built in. And it also lets you manage and manipulate data really easily.
Right.
So the output of one bit of code can be stored and then used directly as input for the next bit of code, all within the same block of code.
So there's a really nice visual in the paper in Figure 1 where they contrast how a repetitive tool sequence would be handled in CodeAct versus using text or JSON.
Right,
And with CodeAct, you can just use a simple loop.
right.
But with the other approaches, you'd have to issue separate commands for every single input, which is obviously much less efficient.
Exactly. And the paper says this, compared to JSON and text with a predefined format, code inherently supports control and data flow, allowing for the storage of intermediate results as variables for reuse and the composition of multiple tools to perform complex logical operations, e.g., if statements, for loops, with one piece of code. So this ability to combine different tools and build these really complex logical sequences within a single unit of code, it's really a game changer for what LLM agents can do.
Right. It unlocks a whole new level of sophistication.
Absolutely.
So CodeAct seems to give us a much more expressive and flexible framework for these LLM agents.
Yeah.
But how do we actually know if it works? That's where the rigorous testing and benchmarking comes in, right?
Yeah, and this is where the rubber meets the road, right?
Yeah.
How do we know this actually works in practice? So
Right.
the authors did a ton of evaluations
Okay.
to really show the strengths of CodeAct, and they used a well-known benchmark called API Bank,
Okay.
which basically tests how well the AI can do these single isolated tool invocations.
Got it.
But they also created a brand new benchmark called M3 Tool Evil,
Okay.
which is designed specifically for those more complex multi-turn tasks where the agent has to figure out how to use multiple tools strategically and adapt its actions based on the feedback it gets along the way.
Okay, so let's talk about the API Bank results first.
Okay.
How did CodeAct compare to the traditional, text and JSON action formats for these single tool calls?
So what's really interesting here is that on API Bank, CodeAct generally did either as well as or even better than text and JSON.
Okay.
And they tested this on 17 different LLMs.
Wow.
So both open source and commercial models. And what was really interesting was that the performance gains were often more obvious with the open source LLMs, which suggests that there might be something about the way these models are trained on code that makes them work particularly well with CodeAct.
Right, so their pre-training on code might be giving them a real edge here.
Eggs.
Now let's talk about the M3 tool evil benchmark, because this seems like the real test for whether CodeAct can handle these more complex multi-step tasks. What did they find there?
Yeah, this is where it gets really interesting.
Hmm.
So when they tested on these harder tasks, M3 tool eval consistently showed that CodeAct had much higher success rates, meaning it completed the tasks more often, and it needed fewer turns, fewer rounds of interaction to do it.
Okay.
And this was true across most of the LLMs they tested.
Wow.
And this really shows us that that flexibility of CodeAct, the way it handles complex logic, really pays off in these more real-world scenarios. So for our listeners, the point here is that this isn't just like a tiny improvement. It's a fundamental change in the kinds of tasks these agents can handle effectively.
And the paper points out some pretty impressive improvements for some of the top-performing models, like GPT-4 1106 Preview, which had this massive 20.7% increase in success rate, and it needed 2.1 fewer turns when it was using CodeAct compared to text.
Yeah,
That's a huge efficiency boost.
absolutely. So it's not just doing things better, it's doing them faster as well.
Right.
But they did find this interesting difference between open source and closed source LLMs on M3 Tool Evil,
Okay.
where those closed source models generally did better with CodeAct on these tough tasks.
So that's really interesting because it suggests that even though CodeAct gives us this powerful framework, the LLM itself still matters a lot, especially for these complex multi-step problems that involve like really advanced reasoning and code generation.
Right.
And that brings us to the work they did to help those open source models get better at using CodeAct.
Right.
And this is where CodeActInstruct comes into play.
Yeah.
So what was the motivation behind this and how did they design it?
So the main goal of CodeActInstruct was to address that performance gap
Okay,
that they saw between the open source models and those more advanced models, especially on M3 tool evil.
right.
So they really wanted to find a way to give those open source models the data they needed to take full advantage of CodeAct.
So how did they create this special training data? What exactly is the CodeActInstruct dataset?
So CodeActInstruct is what's called an instruction tuning dataset.
Okay,
And it's made up of about 7,000 examples
okay.
of these multi-turn interactions where the agent is using Python code to work with a bunch of different simulated environments. And the important thing here is that focus on those multi-turn interactions because it lets the model actually learn how to use that feedback from the code it's running.
And where did this training data come from? What kinds of tasks are actually in CodeActInstruct?
So they were really clever about this.
Okay,
They took a bunch of existing, well-respected data sets and adapted them to work with CodeAct.
okay.
So they use Hotpot QA, which is for finding information using a fake search API. They used APPS and math for things that require software packages, like writing code or doing math with a library called SymPy. They used Wiki table question for accessing and understanding tabular data using SQL and Pandas. And then ALF World, which is for following instructions and planning in simulated robot environment.
So it's a really wide range of agent capabilities.
Right.
But I imagine just taking these existing data sets, many of which were probably designed for single interactions, and using them as is wouldn't be enough. You mentioned a really crucial data processing step. So what did they do and why?
Yeah, so they didn't just dump all the data in there. They specifically looked for these challenging instances within the data sets and turned a lot of those single turn problems into multi-turn ones.
Okay.
So the idea was to create situations where the agent has to interact with the environment over multiple steps, learn from the feedback it gets, and maybe even fix its own mistakes along the way.
Right.
And that's what makes this data set so valuable.
Right.
It actually shows the AI how to get better at problem solving through running code.
And the paper even says that they specifically focused on keeping examples where the model first made an error, but then figured out how to fix it in the next steps,
Right.
which seems like a really good way to teach it to learn from its mistakes.
Exactly. The
Right.
paper says this. To achieve this, we selectively preserve those trajectories wherein the model initially encounters errors but rectifies these inaccuracies in later interactions. For these instances, the LLM typically engages in self-reflection following the initial error, thereby proactively enhancing its future actions. So by picking these self-correction examples, they're basically trying to show LLMs how to use that feedback loop from running code to become better problem solvers.
That's amazing. So now they have this targeted data set of multi-turn CodeAct interactions. What do they do next? This is where CodeActAgent comes in, right?
Right, so this is where we actually see those ideas put into practice.
Okay.
So they took this CodeActInstruct dataset and they used it to fine-tune existing open source LLMs.
Okay.
specifically Llama2 7B and Mistral 7B.
Okay.
And they also included some general conversation data in the mix.
So why did they include that general conversation data along with the CodeAct-specific instructions?
So the thinking was that while they wanted to make the model really good at using CodeAct, they didn't want to lose that ability to have like natural and coherent conversations with humans.
Got it.
So the goal was to make an agent that can understand and respond to human instructions, but also effectively act in its environment by writing and executing code. So it's like finding a balance between like task-specific skills and just being able to talk to people normally.
Right. You want an agent that can both do things and communicate clearly with humans. So how did CodeActAgent actually perform in the tests? Did this fine-tuning on CodeActInstruct actually work?
The results were really promising.
Okay.
So on the Mistral benchmark, which is specifically for testing these multi-turn interactions with tools, both the Llama 2 and Mistral versions of CodeActAgent did better than other open source LLMs that were tested.
Okay.
And the Mistral version even got really good results on that tough M3 tool evil benchmark, almost as good as much larger, commercial models,
Wow.
which shows how powerful that CodeActInstruct data is for boosting these open source models.
That's impressive, especially for a 7 billion parameter model.
Right.
What about the Llama 2 version? Did it show similar improvements on the M3 tool evil benchmark?
So it's interesting. The paper says that the Llama 2 version didn't improve quite as much on M3 tool evil as the Mistral one did.
Okay.
They offer some possible reasons for this in the appendix of the paper, but basically it seems like the Mistral model got more out of that CodeActInstruct fine-tuning when it came to those really complex multi-turn tasks.
That's fascinating. So it seems like there might be some inherent differences between those two open source models, either in their architecture or how they were pre-trained, that influenced how they responded to that specialized training data.
Right, exactly.
And you mentioned this really interesting finding, that the Llama 2-based CodeAct agent was surprisingly good at different types of agent tasks,
Right.
specifically text-based ones.
Yeah, this was really unexpected, but potentially very important.
Okay.
Even though it was mostly trained on this CodeAct data, the Llama 2 version of CodeActAgent actually did about as well as models that were specifically trained for text-based actions when they were tested on these tasks that used.
So let's zoom out a bit and put this work into context within the larger world of LLM agent research.
Okay.
You mentioned some related efforts in your notes. So how does CodeAct compare to what's already out there?
So the paper does a nice job of comparing CodeAct to other research on these action modules for LLMs.
Okay.
And, those use all kinds of formats, text, JSON, different kinds of code.
Whoa, did someone just break the fourth wall? Let's hear it. Oh, absolutely. Thanks for the heads, Zhang. Let's bring this to a close.
Yeah, we can definitely summarize the key points in the time we have left.
So as we were just saying, it was surprising that the Llama 2 model, even with CodeAct training, did so well on text-based tasks.
Right, and this hints that maybe CodeAct helps these models become better agents overall, not just with code.
Exactly. And when we look at how CodeAct compares to other research,
The big thing is that dynamic adjustment of actions based on feedback.
yeah, that ability to learn and refine over multiple turns is a key difference.
And when we think about the future, the potential for more capable AI assistants is really exciting.
Absolutely. Agents that can tackle complex problems in new and innovative ways.
Of course, we also need to keep focusing on safety as these capabilities grow.
Definitely a crucial area for ongoing research and development.
So the main takeaway is that CodeAct, by using executable code for actions,
Offers a more flexible and powerful way for AI to interact with the world.
it's a significant step toward more autonomous and capable AI agents.
Well, this has been a fascinating discussion. Thanks so much for joining us.
Yes, thank you for being here and for the reminder. It was great to share this with you.